Hey guys, this is the Magician, and today I'll be explaining how to evaluate limits analytically. So the main thing you gotta focus on for these theorems that I'm about to show you is direct substitution. Most of them apply that. So if you have limit of b as x approaches c, it's just gonna be b. There's nothing to plug in here. It's like if y equals 4, every point is gonna approach 4. Now limit of x as x approaches c is just gonna be c. You just plug it in. So limit of x to the nth power as x approaches c will just be c to the n. Now some properties of limits that you should know. Let limit of f of x as x approaches c equal L, and limit of g of x as x approaches c equal K. If you're multiplying by a scalar multiple of b, it comes in the limit as well, because limits can be distributed among anything. So we have sum or difference as well. So if we add the two functions and do the limit, it's just the two limits individually added up, L plus or minus K. Now, if we do product, you just multiply the limits. Quotient divide, given that K doesn't equal 0 because dividing by 0 is undefined. And then we have the function to the nth power. It would just be L to the nth power. And then for limits of polynomial and rational functions, this is kind of the same thing, but if you just plug it in again. So limit of p of x as x approaches c just becomes p of c. Another example is kind of like the division here over here. If you have, like, let's say p of x, r of x equals p of x over q of x, and q of c doesn't equal 0, you can do this limit of r of x, just plug in r of c, do p of c over q of c. You just plug in c for x. Now, for radical, same thing, limit of the nth root of x as x approaches c, just going to be the nth root of c. Now, some more that I have here is a limit of a composite function. Now, for these, you basically, if you have a function inside a function, okay? So if you have limit of f of g of x as x approaches c, it's just going to be f of g of c. And if g of c is L, then it's just going to be f of L. So you can distribute the limit inside a function. Now, we're talking about the limits of trig functions. These ones are also easy. Given that it's in the domain, you literally just plug it in. So sine of c, cotan of c, cosine of c, secant of c, tan c, and cosecant c. And there's ones that are like functions that agree at all but one point. So if you have two functions, this is like what I was talking about earlier, manipulating the function if you haven't divided by 0. Now, if you look here, these two graphs are the exact same, but there's a hole here, because if you plug in 1, you get 0 over 0. If you plug in 1 here, you get 3. So basically, this was divided out. X cubed minus 1 over x minus 1 is the same thing. So that's a way to evaluate the limit by substitution. And those two limits would be the same because they're the same function essentially. Lastly, we have the squeeze theorem. And the squeeze theorem is actually pretty simple. It may look kind of difficult just looking at this, but if you have h of x, f of x, and g of x, so let's say we have, and g of x is the largest, so let's say we have the graph right here, and then for this graph, let's say we have g of x at the top, so let's say this is g of x right here. And then let's say f of x is slightly under it, like this. And then let's say h of x was like this, okay? So g of x, f of x, and h of x. Now, they all approach this value. Let's call that, okay, let's say, let's say this is c. And this value is, let's say it's 4, okay? If this approaches 4, then the middle one has to approach 4, right? So it's basically saying if the outer bounds, like basically the function that's larger and a function that's lower, if they both approach a value L, then the limit inside also approaches L. And we'll see that with this final limit that I had to prove, this is true. Limit of sine of x over x as x approaches 0 is 1, and limit of 1 minus cosine x over x as x approaches 0 equals, this should be 0, yeah. So there's proofs for separate of these, but I'm going to prove this one first. So first we have a triangle, like right here from a unit circle. This unit is 1. This is cosine theta, sine theta, 1 tan theta. Okay? Now you have an area of a triangle, area of a sector, and area of another triangle. Basically, this is the biggest area, right? This is the biggest area, then comes the sector, and then the small triangle is the lowest area. So this would be tan theta divided by 2, because that's triangle area. Area of a sector is just 1/2 r squared theta, but r is 1 in all these cases. So it's just going to be theta over 2. And then the last one, this is going to be the smallest area. It would just be sine theta times 1 divided by 2. So just sine theta over 2. Now, if you multiply all these by 2 over sine theta, you get 1 over cosine theta is greater than theta over sine theta, which is greater than or equal to 1. Now, if you take the reciprocal of these, and obviously when you take the reciprocal, you change the inequality, because 1 is less than 4. But if you do 1 over 1, which is 1, 1 is greater than or equal to 1/4. So that's why you switch the sign. And you see how cosine theta is an outer region, 1 is an outer region, sine theta over theta is the middle region. We can apply the squeeze theorem. Since cosine theta as theta approaches 0 is 1, and we talked about a constant, just c, you would just plug that in right there. If limit of 1 as theta approaches 0 is also 1, then you can say the middle one, the limit of sine theta over theta as theta approaches 0 equals 1. There would be a proof for the cosine one as well. I just didn't do that for this. Then the strategy for limit, the general strategy is direct substitution. If that doesn't work, find another function to agree with it, basically algebraic manipulation, so divide it or something like that. And then use a graph or table to reinforce the conclusion. Now we're just going to do a couple questions on each of these types. They'll be pretty easy. Let's start with a simple limit, like limit of 3 as x approaches 2. What does that even equal? Just 3. Now if you do limit of x as x approaches -4, you're going to get -4. Now what if we do limit of x squared as x approaches 2? Plug it in, you get 4. 2 squared is 4. Okay, you get 3, -4, and 4 for these respective limits. Now, another one we can do is, let's say we'll go a little more difficult. Limit of 4x squared plus 3 as x approaches 2. You plug it in, 4 times 2 squared, so 4 times 4 is 16, plus the 3, you're going to get 19. You just literally plug it in. Now, let's do one where you divide it out. Let's do one with a polynomial, but we don't need to divide out. So we'll do limit of x squared plus x plus 2 over x plus 1. Plug in 1, check it. You get 1 plus 1 plus 1, 1 plus 1 plus 2, which is 4. Then 1 plus 1 is 2. You get 4 over 2, which is just 2. Okay, and now let's do the radicals. Limit of square root of x squared plus 4 as x approaches 0, and limit of the cube root of 2x squared minus 10 as x approaches 3. Now, for these ones, you plug them in. Here you'll get 0 plus 4, square root of that is 2. This first one's 2. Now you plug in 3. 3 squared is 9. 9 times 2 is 18. 18 minus 10 is 8. Cube root of 8 is going to be 2. Now let's do some trig ones. Okay? We'll do limit of tan of x as x approaches 0. We'll do limit of cosine x as x approaches pi. And we'll do a limit of sine squared x as x approaches 0. Now, for each one of these, you would plug it in. So tan 0 is 0. Pi cosine pi would literally be negative pi, because cosine pi would be -1, and -1 times pi is just negative pi. And then 0 squared here would be 0. Now let's do one where we divide out with the limit x cubed minus 1 over x minus 1. Now for this, you just factor it out really as x approaches, let's say, 1. Now for this one, it just becomes, the top becomes x minus 1 times x, well, you keep the limit here. So limit as x approaches 1, x minus 1 on the top and on the bottom, but x minus 1 times x squared plus x minus 1. And after that, you factor out the x minus 1, and you plug in, you can just get 3. 1 plus 1 plus 1 here. This should be a plus. So 3. And then let's do another one where it's kind of similar, where we have limit of x squared plus x minus 6 over x plus 3. And we have the limit of x approaches negative as x approaches negative 3. Now, just divide it out. You will get actually 0 over 0 when you plug that in. But one thing you can do is factor out. This is the same thing as limit of x approaches negative 3 of x plus 3 times x minus 2. And then you get still x plus 3 in the bottom. The x plus 3's cancel out. Negative 3 minus 2 is negative 5. Now let's do one where you have to rationalize. That's another technique that we have. So we have, let's say, limit as x approaches 0 of square root of x plus 1 minus 1 over x. Now, to rationalize, you just multiply by the conjugate. So one thing you can do is multiply by the square root of x plus 1. And we're not really doing anything here because you multiply by the top and the bottom by the same. You're just multiplying by 1, essentially. Now, for this, you can make this will simplify to x plus 1 minus 1 on the top, which is just going to be x. And then on the bottom, we have the x and then square root of x plus 1 in parentheses. Perfect. Now the x's cancel out. This is essentially 1 on the top. If you do 0 plus 1, it's 1. Square root of 1 is 1. 1 plus 1 is 2. And then on top you have 1. So 1 over 2, that's going to be 1/2. Now let's do last two trig ones, and then I guess we're done. So we'll do the limit of x approaches 0, at limit of tan x over x as x approaches 0. Now for this one, it's really a combination of kind of what we've done before. You would just, what is this? You can just simplify this to a different function. You have sine x over x, and then you have 1 over cosine x. And basically for that, you would just plug in, because it's just two functions multiplying. You plug in the first part, you get 1. But so if you just do sine x over x, we discussed earlier that's 1. And if you plug that into 1 over cosine x, that's also 1. So 1 times 1 is just 1. So you're actually going to get 1. That's pretty much it. Now, one last question, where we have limit of sine of 4x over x as x approaches 0. Now, for this one, this and this have to equal in order to say 1, right? But no, this is 4x and this is x. Well, what you can do, you can multiply 4 over 4, and you get, what do you get? Limit as a 4 sine 4x over 4x as x approaches 0. And look at this. You can make it kind of you can manipulate it, basically, what our theorem says. So let's set u equal, or u or y, you can kind of use anything you really want. But let's set u equal to 4x. So since we have to put in u, x becomes u now, and instead of 0, it's still going to be 0, because 4 times 0 is 0. So you get limit of u approaches 0 of 4 sine u over u. Sine u over u, that's going to be 1 times the 4, because 1 times 4 is 4. This would be the limit. So it's 4 times sine u over u. Sine u over u is 1, so 4 times 1. 4 would be your answer, and that's it. Thanks for watching.